Okay. Looks like we're in business. I'm glad they let us shut the door now. I knew the university, being very traditional, didn't want us all to die of COVID. They wanted us to die of pneumonia, the old-fashioned way. But I'm very glad I don't have to wear this coat anymore. Okay, so what I'm doing, so last time we started with logic in English, nice easy start. Now we're going to get a teeny tiny bit harder because we're talking about propositional logic, but you've had that already because you saw it in discrete maths and you even saw it in hardware. It'll get harder later, don't worry. And partly, of course, in this lecture, I'll at least set up, some standard notation that we'll use in the rest of the course. And I think there will even be a few new ideas here for you anyway. So when we say propositional logic, and of course the name sounds very grand, but it's just Boolean logic. You're already familiar with it. You've got your true and your false, your and or not, implies if and only if. Because we're not hardware, we don't talk about exclusive or, though you could. In fact, oh dear, there's a thing called the Sheffer stroke. If you Google it, I think it's something like nor, but you see, it's the same thing. You can only do so much with true and false with two inputs. So this is the notation we'll use, by the way, and it really is exactly the thing you've known already. Why do they call it propositional? Well, your guess is as good as mine. There's one little detail. This is, again, a very boring thing, but it's a kind of little detail that can trip you up. So when we use things like P, Q, and R, these are normally fixed things with a fixed meaning. Whereas when I use A and B, like here, I mean these to be effectively standing for any formula. So here I'm saying A, for any formulas A and B, you can have A if and only if B is a proposition. One particular proposition is P. Now, P is a very boring name for a property, but, if you don't have any imagination, you will give your properties names like P. Or, you could choose something more interesting. Okay, as for the semantics, so remember, we're computer scientists. First, we worry about syntax, which is how you write the thing. And next, we worry about semantics, which is what it means. And because it's Boolean logic, it is super easy. The meaning of a Boolean formula is either 0 or 1. Right? It doesn't get much easier. Yeah, everything could be 0. That's easier, but that's not very interesting, is it? Okay, so everything is going to have either 0 or 1 as its meaning. And this, of course, is the truth tables you've surely seen already in hardware, giving the meaning of these particular logical symbols or logical signs or logical connectors, they might be called. So, for example, A if and only if B, the value of that you can read off in this column here, depending on the values. And I nearly called them inputs because the hardware, I'm a computer scientist too, right? So the meanings of these connectors are simply given by a table, which we call a truth table. Now it turns out later that there are things you can write in logic where the meaning does not come from a truth table. So this mysterious box A there, which we get to in lecture 11, is not, the meaning does not come from a truth table at all. This, which you should read perhaps as necessarily A, will have this weird semantical thing involving multiple worlds, and it's a much more complicated beastie altogether. And in fact, even for Boolean logic, things can get much more complicated than this if you go into some weird and wonderful things like constructive logic, which many computer scientists do, the more theoretical ones. Okay, now continuing with semantics. And remember, the last time I said I'm going to show you lots of things like, I don't know, satisfiability, entailment, interpretations, first in English, and then I will specialize them to our different formalisms. So now we have a formalism, which is propositional logic. Now we can talk about interpretations here. So remember, you need interpretations as soon as you have variable symbols of some kind in your formulas, because you have to give meanings to these variables before you can evaluate the thing. Now, in this case, a propositional variable is something like P or Q, and the only values they can have are 0 and 1. So all an interpretation has to do is map each propositional letter to 0 or 1. So it's just a function. And now we say, so I is such a function. Now we talk about A being true under the interpretation I, which we can write like this. So A is true under interpretation I, meaning that when you plug in those particular values for your propositional variables, the thing evaluates to true using the truth tables we just saw in the previous slide. What if it always evaluates to true? That is, with every interpretation makes it true. Then it is something like P or not P, which in the truth tables, you can just check in the truth tables for every combination, it will come out to be true. So in that case, we don't need to write any particular interpretation there because it's true in all interpretations. And then we call it a valid formula or tautology. Now, as for satisfiable, it's actually the same as in the last lecture. So satisfiable means there's an interpretation that makes it true, which in the case of propositional logic, we're just using this idea of an interpretation, a function into 0 and 1, and then if the thing exists that makes it come out true, then it's satisfiable. Okay, so nothing very deep here. Now, I want to, and I'm sorry there's so much time devoted to really basic notation, but you see, all these formalisms are a kind of crazy game. And as you know, whenever you play any game, you have to obey the rules. If you don't follow the rules, you lost, even if you're a better player than the other guy because you cheated, right? Or you didn't know the rules. So getting all these things exactly right is necessary. So, and also understanding the meaning of things that look basically the same. Because many things here look basically the same, and it's hard to tell them apart. Like, A implies B. You might say this means if A then B. You might feel there's some kind of causal connection between A and B. And yet, if you look at the truth tables, it turns out it's exactly the same as not A or B. I have a whole slide on that, which is coming in a moment. But for us, we are using what is sometimes called classical logic, and in classical logic, these two are indeed absolutely identical in meaning. Okay? What about this? Doesn't this also sort of mean if A then B? Well, yes, it does, but this is the relation between formulas. See, A implies B is part of the language itself. So this little arrow here is part of the language of propositional logic, and if I write a thing with a lot of arrows in it, it's a propositional formula. This thing, on the other hand, this symbol is not part of propositional logic. So it is outside logic. Now here we are expressing a relationship between two formulas. So we're saying if this formula, any interpretation that makes this formula true, makes that formula true, and the thing as a whole, A entails B, this is not a propositional formula. This is just something in the symbolic language of mathematics. So I guess in general, if you've done some maths, as of course you all have, you see an awful lot of symbolism. And I need to stress that when we make a logical formalism like propositional logic, that is not the same thing as all the symbols you see in a math book, because those symbols are used in a semi-formal way, intermixed with English all over the place. Whereas when we are doing something in a formal logical calculus, you have to write it exactly as it is, and it is a mathematical object in its own right. And so incidentally, going back a line, I've said that A implies B and not A or B have exactly the same semantics in propositional logic. Nevertheless, they are different formulas. And if I ask you to prove this in a certain calculus, and you begin by turning it into that, you've probably cheated, because they are different syntactically. They're different, you see. Depends on which proof system. There are some proof systems in which the first thing you do is turn this into that. But there are others in which they are all treated separately. Now, it's a little fact here, just to, I hope, ease the general feeling of annoyance you're all feeling at the moment. These things are connected somewhat. So when I say A entails B, it turns out this is true if and only if the formula A implies B is valid. Now, why is that true? It simply means in both cases, for every interpretation, if A evaluates to true, then B evaluates to true, which in the second case, this comes out through the truth table for implies. So sorry for this long aside. Now, what is the second half of the slide? It's the exact same thing, except here I'm using a different symbol. I don't believe we've seen this symbol yet. So this symbol is the entails relation in both directions. So it means A entails B and B entails A. In other words, A and B are logically equivalent. As with entails, it's not part of propositional logic. It's outside the propositional logic, and it's expressing a relation between two formulas. Nevertheless, we have, just as we had that bottom line up there, we have this bottom line here. If two formulas are logically equivalent, then it turns out that A, if and only if B, will be valid, and the other way around. Now, before COVID struck, and I had two visualizers, and certainly before I had to pre-record stuff, I would at this moment go from that visualizer to this one. You see that one doesn't exist anymore. And do a long aside, kind of beautifully impromptu on overheads to talk about a thing, but I couldn't do that pre-recorded, and I still can't do it because you see this other visualizer is lying in a heap down there. So what you have to do is pretend that I have walked from here over to here and mention that this next three slides, are not examinable, but I hope they're interesting and stimulating even so. And the reason I have to stress they're not examinable is not so that you don't have to remember 3 slides, but more, I don't want you to get completely confused, because the stuff on these 3 slides is completely different from the way everything else is going to work. So I'm giving you a peek into another world, which is, however, not our own world. So, and this other world is a world in which we really care about the problem here. When you really say A implies B must mean more than not A or B, and your traditional truth tables are wrong. Well, where do we end up? Of course, A implies B generally. There's about an idea of causation here. So if somebody is lying next to a lot of empty whiskey bottles, then he is drunk. So there's a connection, right? There's a logical connection between the empty whiskey bottle and the drunk. So you say, yes, implies. Whereas some kind of, let's say, if he is lying on a fancy sofa, then he is drunk. even if it happened to be true. So if you looked at a lot of pictures of people and all the drunks were lying on fancy sofas, it doesn't somehow have the same meaning because there's no causation. So what are the different approaches to this? And they call it material implication, is the idea that implication is just given by the truth table. One of the things that people object to is, for example, this first formula, P implies Q implies P. If you look at that in the truth table, in other words, you just evaluate all four combinations of P and Q in the truth table, it turns out it's a tautology. And then if you look at it from the point of view of causation, you're going to think, what? If P, then Q implies P. No, that's just stupid, because if P, then P is true, and whatever Q is, P will be true anyway, like BFD. Another aside, when I was at Caltech, you write QED at the end of a proof, but if the proof is trivial, you write BFD instead. B stands for big and D stands for deal, and I'm not allowed to say, okay. Or this thing here, so P implies Q or Q implies R. Again, the truth tables, it comes out to be true, and yet logically it makes no sense at all. So why should it, if you're thinking of causation, this is saying for every P and R, and any Q that you can come up with, either P implies Q or Q implies R, it makes no sense intuitively. So, there's a thing called relevance logic. I won't say any more about it than its name. There is, and if you become a philosopher, you can destroy a lot of trees. I won't say for nothing, but certainly I probably won't read what you've written. But the much more interesting thing is what leads into constructive type theory. Now, when we get to lecture 11, we will look at modal logic, and there is actually a way of treating implication there with the help of so-called modalities to express that the implication of A and B is, in a sense, a universal one. However, the thing which is interesting to computer scientists, again, this is not examinable, but I hope interesting, is this propositionist types thing. Actually, you will, if you do types in part 2, you will see this again, and then it will be examinable. The idea that a proposition is not just true or false, but is somehow contains evidence of something or other being true. So instead of saying A is a formula and this formula is true, you say, okay, A is some kind of proposition, some kind of statement, and little a is something that I can understand as evidence that big A is true. And you can write it like this, and now you see it looks like a typing relation. So little a has type A. And where it gets cool is you say, for example, suppose I have evidence for A and I have evidence for B. I could create the ordered pair of little a and little b. Now I have both of them packaged up, and surely that's evidence for, if you remember your discrete maths, what's a Cartesian product? It's a pairs of elements from big A and elements from big B. And yet, this also looks like we're treating this like conjunction, because you can read this as, if A is true and if B is true, then A and B is true. So this is the idea that this Cartesian product of two types somehow is behaving like the conjunction of two propositions. You can do this for or as well. So I guess if you remember what a disjoint sum is, I'm sure you had this in discrete maths as well. So the disjoint sum of two types, you have a way of injecting from elements of the first type into the disjoint sum, also from elements of the second type into the disjoint sum. And this is behaving exactly like the OR of A and B. And the most interesting of all, and here's now where we connect up with the implication that I have been talking about. Let's suppose that I have a function f, and f of x is in B whenever x is in A. So now I have our notion of causation. For every x belonging to A, f of x gives me something in B. So A being true is causing B to be true. Suddenly I have a very natural explanation of implication as a function, somehow a function that can map evidence for A into evidence for B. And now implication is behaving like a function type, and it's kind of a nice coincidence for us that we use the same symbol for both implication and function types. So this is a little hint of the propositions as types, which it turns out also works for quantifiers, and in fact in a very neat and compact way. And this then connects into oodles of things in, as I said, constructive type theory is a branch of computational logic that is not really in this course, apart from this couple of lectures here. Now, I guess my third slide on this is to tell you why we're not doing it in this course. I think the title says it all, constructive logic being weird, because, well, there's good and bad properties of constructive logic. Now, one of the good properties of constructive logic is whenever you are able to prove A or B, you know which one it is. Now, this is quite a strong property. Indeed, this is an idea of constructiveness, that you don't simply say one of them is true, but you know which. On the other hand, that means you no longer have A or not A, this excluded middle, which for most people is like the most obvious thing you could possibly imagine. So you cannot have this very strong property on the left and still want A or not A to be a tautology. In fact, it goes, yes, we're not talking about quantifiers yet, but we will get to them in a couple of days. If, in constructive logic, if you prove there exists something having a certain property, then you know the value of x. Now, it is quite easy to write a proof in which you can prove the existence of a thing without having any idea what the value is. And clearly that's what mathematicians call a non-constructive proof. So that is, on the plus side, this is a nice strong property. But against it is, you've already, I think, seen last year that existence for all are dual operators, and you can express one in terms of the other. That now will fail with constructive logic. And of course, the thing which got us here in the first place, in constructive logic, the implication is not at all the same as the disjunction. Remember now, for this system, implication will be a function mapping A into B, whereas this disjunction will be either evidence that A is false or evidence that B is true, a completely different thing. Now, what's interesting is that this second one, of the so-called paradoxes, neither is a paradox. This second one is true even in constructive logic. It may be a stupid formula, but it is a true, valid formula. The first one here, however, P implies Q or Q implies R, that is not a tautology in constructive logic. In a word, why don't we do this in this course apart from these slides? And the answer is because just about everything I'm about to show you will not work anymore. So it's much harder to do theorem proving in constructive logic. It can be done. Loads of people are doing it, but it is a lot harder. Is that legible? I hope it's legible. I want to go back to boring stuff again. So we are going to use a lot of techniques for the algorithmic methods I'm about to show you. We need to learn. You've seen all these things before. We will be using them. That's why I'm kind of drawing them to your attention again. So we're going to do a lot of what you could call pre-processing or compiling of logical formulas into very simple normal forms in order to apply this or that algorithm to them. So we just need to remind ourselves of the kinds of equivalences that are true in propositional logic. And remember, you kick all that constructive stuff away because we're done with it forever, actually, till part 2. And I don't teach that. Okay, so some very obvious things here. You know this one, commutativity. You know that one, associative law. All of them straightforward. This one is slightly weird. You see, you all learned in school how to multiply out brackets, and you can probably do it standing on your head. That will help you somewhat in manipulating logical formulas as well. So you'll say and is like multiplication and or is like addition. And that works everywhere except here, because you see this is a distributive law that doesn't work for polynomials, right? So this is actually true, although that is an or on the outside and the and on the inside, and we can push it in like that. And not only can we do this, but this is one of the most important equivalences we're going to have in this course. So you do need to understand that it's true, and we're going to use it, and soon. Actually, I don't like the kind of, shall we say, exam question or work that forces you to cover the page with calculations of this on this level, because it's kind of stupid. But you never know what might turn up. Okay, so, and there are a few more. Now, I used to have a second slide, but I noticed, you see, we have a very strong property in classical logic, not this constructive logic, of duality. We can exchange and with or, true with false, in any of those, and we get another equivalence which is also valid. This often means that we can cut in half the amount of stuff that we need to know about. So as it is here, so this duality means, for example, that this thing is true with or, and so is that one, and so is that one. Here it's true if you exchange the ands and the ors, and so on. So we have all these equivalences, but this one here in the middle, this distributive law, is perhaps the most important. Also worth noting are these two, especially the first one. So think about it. A or B implies C. So thinking about the drunk guy here, see, an empty whiskey bottle implies he's drunk, but like 2 empty wine bottles also imply he's drunk, you see. So anyone who has either a whiskey bottle or 2 wine bottles is drunk. You can think of it in that term. I'm going to get in a lot of trouble later for using these examples. And we will see this kind of reasoning about disjunction implies something we're going to see very soon. This second one is perhaps not so remarkable. Okay, so anyway, those are some equivalences to know about. Okay, as I just said, a lot of the time we're going to be compiling things into normal forms. And what are they? Well, I have too much stuff here on this slide. Well, let me start on that half. Sorry, I'm contradicting myself. You see, logical symbolism, and indeed mathematical symbols in general, were invented in order to help people express themselves more clearly. And of course, as I've said already, they were originally semi-formal mixed with English and so on. And there is some early manuscript in which you can see the invention of the plus sign and the equal sign, and it's kind of cute because they're both really long. It's like 1 plus really long horizontal thing and a little thing. 1 equals like really long 2, you know. And then they kind of tidied up their notation after that. Now we have fully formal logical calculi, which are still trying to be legible, and so they have a lot of stuff they don't really need. So this so-called Sheffer stroke, which I mentioned and which I think is equivalent to NOR, maybe it's NAND, it doesn't actually matter. Whichever one it is, it replaces all the logical symbols we normally use, you know, and or not, if and only if can all be expressed in terms of NOR, but everyone would hate you. So we're trying to be natural when we have these supposedly intuitive symbols. That's why we don't use exclusive OR in logical formulas, because, okay, exclusive OR is great in hardware because it adds things, but in terms of expressing mathematical properties, it's generally not what you want, whereas if and only if is a thing we use all the time. So we have these languages which have a lot of redundancy in them, and they're not very, I mean, they're just redundant, and what we are trying to do then is to compile them down into something really simple. So one of these normal forms is this negation normal form, which we'll see in a moment. It still leaves a certain amount of structure. If we want to get really brutal, we can go to conjunctive normal form. And finally, there's things like clause form, and in fact, there's a number of others. And the point then is very analogous to compilation of a high-level language into assembly language. So you keep removing structure, making things more uniform, and then allowing simpler algorithms. And unfortunately, each stage can allow exponential growth. So already here, you can get an exponentially larger formula. Then again, you can get exponentially larger again. And this is kind of unfortunate, but let's face it, everything we do here is at least NP complete, if not undecidable. So what is negation normal form? There's really nothing to it. And the idea of negation normal form is that we have we have only trivial negations. The first step is to get rid of the implies and if and only if, because both of them have a kind of implicit negation in them from the truth table. Certainly remember, implies is not A or B, so there's a negation there. So we need to expand them out. And remember, A, if and only if B can be expanded out like that. In fact, it can also be expanded out as A and B, or not A and not B. And if you're super clever, you will use either this one or the other one, depending on other stuff. A implies B, of course, can also be expanded out. That's just the first step. And the second step is simply to push the negations in using De Morgan's laws. Again, this is a thing you already could not do if you were using constructive logic, which is why we're not doing it. You've seen these all before, right? So the point of this is that you have pushed all your negations inside, and negation is now only applied to propositional letters like P, Q, R, and nowhere else. So there's no negation applied to a bigger formula. So the point of negation normal form, as I said, each normal form is trying to eliminate some redundancy and give you a simpler structure. So here, your formula will consist only of ands and ors combined together with maybe a bunch of negations at the bottom. actually, we won't really be using negation normal form in this course. We will be continuing, or rather we will be using it only as a way station to conjunctive normal form, which we'll be using a lot. So if you want to go to conjunctive normal form, first you convert to negation normal form, and then you can continue. Now, what is conjunctive normal form? It's when your formula is just a conjunction at the top level. The next level down, that is the things you are anding together, they are all disjunctions. And finally, at the bottom level, the things that are being ordered together in those disjunctions are so-called literal, so they're either propositional letters or the negation of them. Now, how do we do this? Well, all we need to do to get from negation normal form to conjunctive normal form is to, well, the point about conjunctive normal form is you want the ands on the outside. So whenever you see an and not on the outside, you need to do something about it. So you have this case and the other case there. If and is not on the outside, you use the distributive law I just showed you to push the disjunction inside. There you see we bring the conjunction to the outside and we have pushed the disjunctions down. And I hope you can see where the exponential growth comes from. On the left side we have one copy of A, and on the right side we have two copies of A. So I don't teach foundations of computer science anymore, so I hope whoever did teach you reminded you that anything that grows exponentially is probably going to get you into a lot of trouble. Yes? In fact, we can thank COVID for a 2-year lesson on what exponential growth does, right? If anyone still doesn't know what exponential growth is like, there's no excuse for it. So you might say then, if this is so bad, why do we use it? And the answer is, in fact, so often in computer science, the worst case is not what we get. But secondly, there are some clever tricks one can use to eliminate the exponential growth, or at least to bring it under a certain control so that most of it doesn't occur. We're not going to see that in this course, however. Okay, having multiplied out, in a sense you are already in conjunctive normal form at this point, at this step 3. The step 4 is to get rid of certain trivialities. So in particular, if you produce the disjunction P or not P, then you can throw that away, because P or not P is trivially true. Remember, we're classical logic, forget the 3 slides. P or not P is trivially true, so it can be simplified down to true, which means since they're all anded together, you can throw it away. The next step, which is trickier and not really strictly necessary, but just to remind you, one can simplify a bit further. So, for example, in this formula here, P or Q and P, this is equivalent to simply P. Why is that? Think for a moment. P is either true or false. If P is true, then the formula P is true. So if P is true, both this formula and the formula P will be true. What happens if P is false? The formula P will be false. This one will also be false because it's anded with P. In general, what's going on here is you've got something here anded with something which is weaker than it, and so this weaker thing is always irrelevant and can be thrown away. And this last one, again, you can check whether, regardless of whether P is true or false, this thing will be equivalent to A. As I said, apart from this first step of simplification, which is completely trivial, these others are a bit more work and not strictly necessary, I guess. Dear. Yeah, here I would normally have written these out. Shall I see if I can do it? Look. The test of whether he is together enough to do, they haven't given, there's paper. It's always fun to watch your lecturer make a fool of himself. So let's see if I can convert that to conjunctive normal form without looking at my own slide. So what would I do here? This is going to be or Q or R. This is going to be the negation. Well, I shouldn't skip steps because if I do, I will definitely make a lot of mistakes. That then is going to be not P and not Q or R. And finally, because I have and inside, I can grab both of those and push them in, and then I get not P or Q or R, anded with not Q or R. And now what do I see? I see a tautology there, so I say goodbye, and is that the answer? Yeah, well, yeah, you see? And as it says on the slide, this is not a tautology, and we can read off a counter example. So when P is true, Q is false, R is false, what happens there? Q or R will evaluate to false, P or Q will evaluate to true, and true implies false, evaluates to false. So we have now a concrete counterexample to that thing. And as I recall, I think I decided to use this formula as an example in some future lectures of different kind of theorem-proving things. Oh dear, can I do this one? This one is totally brutal. Well, again, this will be or P. So the negation of something, that will be or P, I guess, as well. And what is that? It's the negation of that, so that will be, I am sure this is going to go so wrong. So, I should have 3 not signs, and I've only got 2, so I've made a mistake, but wow, then there should be a not there, shouldn't there? That looks better. I still will be amazed if I get the right answer, but you have it on your slide. Now let me see what I can do. So what happens? This has got 3 negations in front, so I assume this will be something like not P or Q. Still, that has got 2 negate. Wait, what am I doing here? Well, look, don't skip steps, right? That will be not P. This will be, okay, push the not in, that will be fine. So that not will cancel out, and I'll have not P or Q here. That would be and not P. I hope I am still right. And then what have I got to do? Well, I've got an or here and an and there. So I will have not P or P. And here I'll have not P or Q or P. And that goes and that goes. So this comes out to true, and I know that at least is the right answer. So I have the right answer even if the working isn't right. So it can be done, although it's annoying. I want to make 1 or 2 last remarks before finishing. So one interesting thing, a very trivial fact of conjunctive normal form. So if I have a formula written in this way, and assume these are non-trivial formulas. So as in the previous example, remember I canceled out the trivial ones that had not P or P in them. So what will be left is only the disjunctions in which all the propositional letters are different. And in such a thing, I can always make false. Just because they're all different letters, I can assign them true or false as necessary to make the whole disjunction false. And because these things are being ANDed together, then I can choose any of them. So I have, if you like, n different ways of making this formula false, because I can pick any of the AI, and in that AI, all the propositional letters are different, so I can choose all of them to make it false. So if by converting a thing into conjunctive normal form, you see in the first example here, I ended up with a counterexample. And in the second example, I had transformed it into true. So this already is a trivial theorem-proving method. It's a lousy one, but it does work. So take any propositional formula, convert it to conjunctive normal form, and you will either convert it to the true, or you will have it in a form where you can exhibit a counterexample. So that's nice to know. A few historical notes. So the dual of conjunctive normal form is a thing called disjunctive normal form, exactly the same thing except you exchange the roles of and or. This can be used to detect contradictory, or I should say unsatisfiable formulas. This was lousy. Now later in the course we are going to see some very powerful ways of working with propositional formulas and detecting whether they are valid or not, which are all in general in exponential time, but in some cases they're very efficient, and in the case of BDDs, are very good at proving the correctness of even very big hardware designs, like very large adders and other devices. One can check effectively instantaneously whether the hardware, whether the design of the gates and so on conforms to the logical description of the device. This SAT-solving methods here have been applied to so many things now, I don't have time to list them all, but I guess I will mention one. So they can approximate the behavior of program execution in terms of finite models, because clearly a program is effectively giving you infinite behaviors, potentially infinite values of everything. You can approximate them in very crude ways, and typically the bugs in programs turn up with very small counterexamples, like 3 times around the loop, and if the loop has a bug in it, the bug will already be evident. So one can automate things in quite a powerful way and turn them into purely propositional problems and solve them very quickly, and a lot of this stuff has been deployed out there. But I need to finish now, so thank you.